Only 1 second, sir. Sir, please, you can start, sir.
Huh?
Yes, sir, you can start now, sir.
Okay. ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. ಗುಡ್ ಈವ್ನಿಂಗ್ ಸ್ಟೂಡೆಂಟ್ಸ್. ಇವತ್ತು ನಮ್ಮೊಂದಿಗೆ ದೀಪ್ತಿ ಮೇಡಮ್ ಅವರಿದ್ದಾರೆ. ಅವರು ಸೆಮಿಕಂಡಕ್ಟರ್ಸ್ ಬಗ್ಗೆ ಉಪನ್ಯಾಸ ನೀಡಿದ್ದಾರೆ. ಉಪನ್ಯಾಸಕ್ಕೆ ಮೊದಲು ಕಿರು ಪರಿಚಯ. ದೀಪ್ತಿ ಅವರು BE ಪದವಿಯನ್ನ PTU ಇಂದ ಪಡೆದಿದ್ದಾರೆ. ಆನಂತರ MTech ಪದವಿಯನ್ನು NMIT ಕಾಲೇಜಿನಿಂದ VT ಕೆಳಗೆ ಬರುತ್ತೆ, ಅಲ್ಲಿ ಪಡೆದಿದ್ದಾರೆ. ಅದಾದ ನಂತರ ನಲ್ಲಿ ಸುಮಾರು 7 ವರ್ಷಗಳ ಕಾಲ ಕಾರ್ಯನಿರ್ವಹಿಸಿದ್ದಾರೆ. ಹಾಗೆ ಈಗ ಪ್ರೆಸೆಂಟ್ಲಿ ಎಡ್ಜ್ ಕ್ಯೂ ಇನ್ಕಾರ್ಪೊರೇಟೆಡ್ ಅನ್ನೋ ಕಂಪನಿಲಿ 2020ರಿಂದ ಕಾರ್ಯನಿರ್ವಹಿಸುತ್ತಿದ್ದಾರೆ. ಅವರು ಹಲವಾರು ಲೇಖನಗಳನ್ನ ರಾಷ್ಟ್ರೀಯ ಮತ್ತು ಅಂತಾರಾಷ್ಟ್ರೀಯ ಮ್ಯಾಗಝೀನ್ಸ್ ಗಳಲ್ಲಿ ಪ್ರಕಟಣೆ ಮಾಡಿದ್ದಾರೆ. 30 ವರ್ಷಗಳ ಅನುಭವ ಇದೆ. ಅಲ್ಲದೆ ಮೇಡಮ್ ಅವರು ಎಕ್ಸಿಕ್ಯೂಟಿವ್ ಕಮಿಟಿ ಮೆಂಬರ್ ಆಫ್ IEEE Nanotech Council. She has been an active member of the various symposia, technical talks and workshops through the council. ಅವರ ಅನುಭವ ಮತ್ತು ಇವತ್ತು ಸೆಮಿಕಂಡಕ್ಟರ್ ಬಗ್ಗೆ ಉಪನ್ಯಾಸವನ್ನ ಇದ್ದಾರೆ. ಸೆಮಿಕಂಡಕ್ಟರ್ಸ್ ಬಗ್ಗೆ ಸೆಕೆಂಡ್ PU ನಲ್ಲಿ ಏನೂ ಇದೆ. ಈ ಒಂದು ಉಪನ್ಯಾಸವನ್ನ ತಾವೆಲ್ಲ ಆಲಿಸಿ. ಕೊನೆಯಲ್ಲಿ ಮೇಡಮ್ 2 ಕ್ವಶನ್ ಕಳಿಸ್ತಾರೆ, ನಿಮ್ಗೆ ಶೇರ್ ಮಾಡ್ತೀವಿ. ಇದರಲ್ಲಿ ಅತ್ಯುತ್ತಮವಾಗಿ ಬರೆದಂತ 2 ಉತ್ತರಗಳಿಗೆ ಎಂದಿನಂತೆ ಬಹುಮಾನ ಇದೆ. ಬ್ಯಾಕ್ಗ್ರೌಂಡ್, I request Deepthi Prasanna to take over and deliver. Over to you.
ಧನ್ಯವಾದಗಳು ಸರ್. Thank you for your kind words and the introduction. Let me see if I can share my screen.
ಸ್ಕ್ರೀನ್ ಕಾಣಿಸ್ತಾ ಇದೆ.
Thank you, sir.
ಕಾಣಿಸ್ತಾ ಇದೆ.
Thank you everyone. Very good evening to one and all, and thank you for joining. Once again, Dr. Ramesh sir ಹಾಗೂ KSTN ಎಲ್ಲ ಸಿಬ್ಬಂದಿ ವರ್ಗದವರಿಗೂ ನನ್ನ ಧನ್ಯವಾದಗಳು ಮತ್ತೊಮ್ಮೆ ಈ ಒಂದು ಆಪರ್ಚುನಿಟಿ ಕೊಟ್ಟಿದ್ದಕ್ಕೆ. So today we shall dive into this world of semiconductors and understand more about its applications and uses, and also try to appreciate how this has become a giant thriving industry. So if we actually look back into what were the key discoveries or inventions which changed the course or which changed the history of mankind, we might say it might be the discovery of fire or the invention of wheel. On the same lines, and if we have to take the modern day world scenario, semiconductors are one such things which have become a game changer in the civilization, in the history of mankind. When I got to know that this semiconductors is a part of PU syllabus, I tried to look it up, and I have also tried to include few parts, few elements of what is already present in your syllabus, so that I can bring some connectivity and make it slightly more relatable for you, for all the students. So about what I'll be talking next. So yeah, let's begin. Before we start off with what are semiconductors, how they work, and what are their uses and applications, first I feel it is very important to understand why are we studying about semiconductors in the first place? Why is it present in your syllabus? Many of you might already have an idea or be familiar with what are semiconductors and their applications. But as this talk is targeted towards a wider range of audience for all the students from different backgrounds, I would like to take this up first as to why semiconductors, what is their importance. There is one common thing which I hear from many students saying, there is something in my syllabus. I have studied it just for the sake of exam. I don't know what are the applications or what are the uses of what I'm studying in my syllabus anymore. Or even worse, there are some students who assume whatever we are studying is of no use in our future as well. That is very wrong. So, if I have to give a very simple example, a simple illustration for this, let's take something which we all have studied in our schools, which is Pythagoras theorem. Now, we have all learned it by heart, Pythagoras theorem, that the hypotenuse c square is equal to a square plus b square, where a and b are the sides of this right angle triangle. So we have studied this, we have probably mugged up the proof, we have written it in our exams, but have we ever given a thought about where exactly this gets used in real life scenarios? Let's take a very simple example. Imagine you're building a house, a multi-storied house. In order to move from one floor to another floor, we would require staircases. And if you see this picture, you can clearly make out a right angle triangle there, wherein the staircases is forming the hypotenuse. So what do we get out of this? We will get what is the elevation required in the staircase. How many number of stairs would be required in order to reach from one floor to another. This is a very simple example, but a very real life use case of Pythagoras theorem. Similarly, geographically, if you are trying to find out the elevation of mountains, or if you're trying to find out the peak of a particular mountain, then again we'll have to apply the same Pythagoras theorem again, the same right angle triangle. Whatever you need to find, if you know the hypotenuse, you can find the sides. If you know the sides, you can find the hypotenuse. You can find the distance from where you are to the tip of the mountain. Many such use cases are actually there for the Pythagoras theorem. Similarly, if we just step back and reconsider what we are studying and try to find out the applications and use cases of what we are studying, we will actually enjoy what we are studying in the first place, which is more important rather than just studying something for the point of exam. So let's get back to semiconductors. Why semiconductors? Now, just pause and look around you. If you just look around you, you will be surrounded by at least 5 of these gadgets around you. You obviously will be having your mobile phones or laptop or computer through which you are being a part of this webinar. Everybody will have usually a TV, a refrigerator, a washing machine. Some people might have a microwave oven, a printer, or some other fancy equipment. So if we just look around us in our day-to-day lives, we are surrounded by electronic gadgets. And all of these electronic gadgets, all of them, not few of them, all of them are made out of semiconductor materials. So semiconductors play a huge role. They're of utmost importance in our day-to-day lives as well. So this was just an example of how it is influencing us in our day-to-day lives. Is this the only applications of electronics? No, we have various applications. It is used in automotive industry. Right now, all the cars that are coming out are mostly having so many smart features like automatic parking assist, or some traffic control, lane control, blind spot detection. There are so many things, which wiper control. Automatically, the wipers will turn on if it starts raining. So there are multiple such things which is making the cars smart these days. Apart from that, healthcare industry, hospitals, there are so many medical equipments and um, imaging. So all the medical equipments, they're all electronic equipments, which are of highest importance in our day-to-day lives. Communication and networking, internet, something which nobody can live without these days. Uh, Communication can be in the form of anything. It can be Bluetooth communication, it can be a wireless communication, which in the form of Wi-Fi, in the form of your mobile phone services like 3G, 4G, or the upcoming 5G. In communication and networking industry, completely, it's dominated by electronics. In the entertainment industry, all the movies, all the music videos, everything that we see from the entertainment industry, they are having a huge influence of digital uh, uh, electronics on them. Of course, robotics, that goes without saying. Robotics have a very high influence again. Online classes, what we are having currently, many of this was not something which was widely popular before COVID, but one of the things COVID brought us together is having the um, opportunity to attend any class or listen to anyone across the globe by sitting at the comfort and safety of your homes. So this has been another revolution in itself. In farming, there are multiple practices, smart practices that have been deployed in farming in order to increase the yields. So these are just few of the multiple applications which electronics has in our day-to-day lives. And like I said, semiconductors are something which have been an integral part of our life, even without our knowledge in all these years. So before we move on, what are the basic requirements in an electronic gadget or an electronic device? We must have good controllability over it. It must not uh, uh, take a huge space. It should be compact. It should be reliable. It should be safe. It should be controlled. Reliability, everything matters. So, one primary important thing that is needed for achieving all these things is the controlled flow of electrons. The controlled flow of electrons is what is making these electronic gadgets work in the first place. So earlier, when we did not have these semiconductor, when we had not yet discovered the potential of the semiconductors, we used to use something called as vacuum tubes. Now, what is a vacuum tube? A vacuum tube will contain a cathode tube, which is, if you see the second diagram below, there is a tube in the middle, which is a cathode tube. There is a grid around it, and that is enclosed by an anode plate. And the whole thing is covered inside a glass envelope. And inside this glass envelope, there is complete vacuum. That's the reason they're called vacuum tubes. Now, what happens here? We supply power to the cathodes and they start emitting electrons, and the anodes will catch them, and the current starts flowing. Now, why do we need vacuum for this reason? Vacuum is required so that the electrons don't collide with any other molecules which are present inside. That's why complete vacuum has to be maintained here. And what is the purpose of the grid? The grid will give you some kind of controllability over the flowing of electrons. Now we can't control how much electrons a cathode will emit, but we can control how many electrons an anode can absorb. So that is achieved using a grid. Now these vacuum tubes were very huge and bulky. So let's take one example here. This is ENIAC. This is the world's first general purpose computer. So ENIAC was almost as big as a room. It was huge. And this deployed 18,000 such vacuum tubes inside it. And this was used during 1945, I guess, during the World War time. And it was used for computing something very simple, but it still required so much space, so many hardware, and it was very tedious. Similarly, this is another example of another supercomputer. Supercomputer in those days, which were huge, which were as big as a building. One computer which now can fit in your palm or in your lap used to be as big as a room earlier. That's because of these vacuum tubes. Now, like I said, they had some advantages as well because they provided somewhat controlled flow of electrons because of the grids. And calculations were definitely faster compared to what an average human would take. But the cons were overriding these pros because they were extremely bulky, they were extremely power hungry. You had to continuously keep supplying power to the cathodes. And because they were continuously being supplied with power, they used to burn out very quickly. So they had very limited lifetime and they had to be replaced also very frequently. This was a pain. And in spite of all of this, the reliability was also very low. So these were the reasons vacuum tubes did not last very long. Though they started out with this, they didn't last very long. Now, let's come to some basics. So as you all know, solids can be classified into conductors, insulators, and semiconductors. Now, what is the difference? Let's take a very simple example of, let's take one atom. Okay. So the energy level of an electron is determined by where the atom is present in which orbit in the atom. Where the electron is present in the atom, in which orbit. So the outermost orbital electrons are called valence electrons. Those valence electrons are the ones which actually conduct, which have more energy and can actually start conducting. Now, this is the case in one atom. But when we take solids, these atoms are jam packed together. There is no space. So, because these are jam packed, we will have different kind of energy levels in different atoms. So, this energy differences are called as band gaps. So, that's where we come to the band gap theories. So in band gap theory, what happens? A conductor will have no space between the valence band and the conduction band. So valence band is something where all the electrons are stable, nothing is conducting. Conducting band is something where the electrons which go to the conduction band will actually start conducting. So if we see a conductor, there is no band gap at all. They are completely overlapping each other. So the electrons can easily move into the conduction band and start conducting. But if we take an insulator, for example, the rightmost diagram here, we see that the valence band and the conduction band are separated by a wide gap. So even if the electrons do escape from the valence band, they cannot go to the conduction band because the gap is too wide. That's the reason they cannot conduct. But if we come down in between to the semiconductor, they can either behave as a conductor or behave as an insulator, depending on how we wish. So if there is a very small narrow band gap between the valence and the conduction band. So once the electron gets excited, it will move from the valence band to the conduction band easily with not much effort, with very less power. So that is the reason semiconductors are chosen to be the manufacturing units of all electronic components, because we have this controllability over it. We can control how it conducts, how much it conducts, when it conducts, everything. So this is the reason we have chosen semiconductors as the manufacturing units. Now, like I said, semiconductors are something which have the conductivity between that of a conductor and an insulator. Now, because it can work as either a conductor or an insulator, it's basically mimicking the operation of a switch. That means it can turn on and start conducting when you supply some power, and it can turn off when you don't need it. This is exactly what we need in our electronic appliances as well. We don't want something to completely keep running, or we don't want something to not run at all. We want it to run when we need it and turn off when we don't need it. So this makes semiconductors an ideal candidate. Now, the commonly used semiconductor is silicon or silica, which is abundantly available as silicon dioxide, or common words, it's called sand, normal sand, which is abundantly available. Out of that silicon dioxide, we will be extracting pure silica, and that will be used as the semiconductor material. Other options we have are germanium, gallium arsenide, cadmium sulfide, indium phosphide. Now, these are all compounds, but purely intrinsic in nature are silicon and germanium. Like I said, vacuum tubes had lot of issues. They were not reliable. They didn't have proper controllability. They were bulky. But semiconductors have the opposite of everything. They are extremely reliable. They have excellent controllability over the conduction. They are low cost because they are abundantly available. They are very compact, lightweighted, have long life, and like vacuum tubes, you don't need separate components. Like you don't need a cathode, one anode, one glass tube, one enclosure, vacuum inside that. Nothing is needed. This is just one simple material which can do everything inside the same material itself. So semiconductors are an ideal choice in this case. Now, semiconductors are used in the manufacture of almost all electronic components, like I said. For example, transistors and diodes. I'm giving these examples because these are something which you would be familiar with. Now, when we take semiconductors, there are two kinds again. There are intrinsic semiconductors and extrinsic semiconductors. Now, let me take only silicon and germanium as an example. They are tetravalent in nature. What is tetravalency? Tetravalent means they have 4 electrons in their outermost orbital. So these 4 electrons need 4 more to become a stable electron. So what they do is they borrow 1 electron from each of their neighboring atoms and they form covalent bonds with them. And once they get 8 electrons, they'll be stable in nature. But if you apply some heat or some excitation, usually it will be heat. That is enough to break the covalent bonds, and the electrons will come out of this bond and start conducting. So this can happen. This can happen even at room temperatures as well. But because these are purely tetravalent in nature, the conductivity that happens in room temperature will be very negligible. At the same time, we want our devices to work in room temperature only. We don't want to supply external heat and heat up our devices. We don't want to give extra power, nothing. We want our devices to work in room temperature. So what can we do to make them conduct better at room temperatures? That is where doping comes into picture. Doping is something like adding some external impurities into the already available tetravalent semiconductor. That will make it an extrinsic semiconductor. For example, like I said, silicon and germanium are tetravalent. We can either borrow the dopants from a trivalent element or from a pentavalent element. Now, if we take trivalent, for example, indium, boron, or aluminium, they will have 3 electrons in the outermost orbital. So there will be one gap, one hole when you mix it with silicon, because silicon has 4. Suppose we take boron, boron will have 3. So there will be one hole which is remaining. So to fill the hole, there will be one electron which will jump into that, and that will create another hole. Then the next electron will jump in. So like that, we will have the movement of a positive carrier here. This will create something called as a p-type semiconductor. In the same lines, if we take a pentavalent impurity like arsenic or phosphorus or antimony, pentavalent impurity will have 5 electrons in its outermost orbital. So if you add that to silicon, there will be one extra electron. So that extra electron will be free to move around. The number of negative charges are more in this. Hence, we call it as a N-type semiconductor. Now we understood how do we create a P-type and a N-type semiconductor. Now, when we put both of these together, P-type and N-type semiconductors together, we form something called as a PN junction. Now, this PN junction is actually the basic building block of all devices like diodes and transistors. How does this work? Let's see in the next slide. Okay, so this is a basic PN junction. We have an N region in the left, a P region in the right. Now, because there is a concentration gradient here, there are only electrons on one side and only holes on the other. They will start moving towards each other so that they can compensate for this gradient. So when they start moving towards each other, that's called diffusion. And because of that, they will also um, leave behind ions. So the negative region will leave behind positive ions, and the P region will leave behind negative ions. These ions will come in the middle and they form something called as a depletion layer. This is actual PN junction, which we are talking about. And this depletion layer is something which will prevent the further movement of electrons by themselves. Now, how do we make this conduct? So now this is acting like an insulator because it's not allowing anything to move. But we want now to turn it into a conductor. So what do? We supply it with some electricity. We forward bias it. If we forward bias, then the depletion region will start decreasing. When the depletion region decreases, the electrons can now start moving from N region to the P region. So this will actually make the PN junction to start conducting. So from what was an insulator, now we have changed into a conductor. So this property of semiconductors is what makes it the most favorable in electronic devices. Now, the PN junction which we just saw right now is commonly called as a diode, which most of you might be familiar about. Now, the same diode, if we have multiple junctions instead of one junction, if we have, say, two junctions, then we form something called as a BJTs, which is a bipolar junction transistor. So, as you see here, there are two junctions between N and P here and N and P here, and the same in the bottom one as well. So we can have multiple variants of it, like NPN and PNP. So based on the use cases, we can either choose an NPN kind of transistor or a PNP kind of transistor. So this again, the basic principle behind the junction and how the depletion makes it an insulator, how forward bias will make it a conductor will remain the same. But the number of junctions have been increased here, that's it. So we get something called as BJTs out of this. Now, BJTs have some challenges of their own. They require more power and they are not very stable. So, we have devised another kind of transistors known as MOS transistors. Now, what is MOS? MOS stands for metal oxide semiconductors. How these MOS transistors are formed and how are they fabricated is another exhaustive topic which will be completely out of syllabus for you. So I would recommend you to study this by yourself if you're interested. But if you take up engineering, electronics and engineering, you'll definitely be studying more about MOS transistors. So I'm just giving a brief overview of what a MOS transistor is. A MOS transistor will basically have a substrate. Substrate is a base layer. A base layer, and it will have two small buckets that you see there here. Those buckets are actually called wells. So there will be one substrate. Inside that, we will dig up wells and we will add the required dopants. So similar to NPN and PNP transistors, here we have NMOS and PMOS transistors. NMOS will have N wells, P substrate, and another N well again. So the same way PMOS transistors will have two P wells inside one N substrate. Now, what happens when we put both of them together, NMOS and PMOS? Then we get something called as a CMOS, which is a complementary metal oxide semiconductor. Now, these CMOSs are something which are the basic building blocks of every electronic component that we see in modern day. This can be analogous to a cell in a human body. We have learned in biology that a cell is a single unit, which is the basic building block of every organs, every tissues in the human body, right? Like that, this CMOS transistor is analogous to a cell, which is the basic building block of every modern day electronic component. All right. So just to make things more interesting, I have a small activity for you guys. I'll be sending this later at the end of the presentation as well, like Ramesh sir mentioned. But this is one question wherein I want you to go back home and do some research on what are the various applications of diodes and transistors. Where are they actually used? If we I mean, I know you all are under tremendous pressure. You'll be having a dozen exams, internals, externals, lab, uh, records, CET coaching, NEET coaching, 101 things. But I would still request all of you to dedicate at least 15 to 30 minutes a day in learning something new, in researching. Take some topic. You have internet which can get you any information from around the world. So do some research on what are you studying, why are you studying, where are they actually applied, where are they actually used. um, there's also another thing that everything you study on the internet might not be true. So what you have to do is just make down points, note down points of what you have studied, and you can approach your teachers or any experts who you think will be able to guide you better. But please do dedicate at least 15 minutes of your time every day in order to research on the use cases of something that you're studying. That will actually make you like the subjects more. All right, so let's move to digital electronics. Now, we understood that transistor is actually the basic building block of every electronic component. Now, what is a digital system actually? The digital system is an assembly of logic gates. Now, what are these logic? I mean, most of you might be familiar with this already. Logic gates are something where the output of this gate is related to the input based on some kind of logic. Now, all of these are the most common and most widely known logic gates. We have the NOT gate, AND gate, OR gate, NAND, NOR, XOR, XNOR, and their truth tables also beside. So how are the outputs depending on the inputs here? Let's take AND gate, for example, the top right one, AND gate. So the how an AND gate works is if both the inputs, if it has two inputs, if both the inputs are 1, then the output will be a high 1. Or else if either of them is 1 or both of them are 0, then the output is always 0. That's why it's called AND gate. Both A and B have to be 1 to have the output as 1. Similarly, if you take an OR gate, the one right below that, in OR gate, you can get the output to be 1 if either A or B or both of them are 1. But if both are 0, it will be 0. So these are the logic based on which the outputs are dependent on the inputs. So these are some basic logic gates which you would have already studied. So what happens in digital electronics is the whole point of having it digital is because it does not have something which continuously happens. Like it's not analog like a sine wave which continuously keeps going up and down. This is either a 1 or a 0. It will either be on or off. That's why all the digital electronic things will translate into a binary logic. You might have heard that computer understands only binary. It can understand only ones and zeros. Why is that? Because the computer contains these things as its hardware, which basically understands only ones and zeros. That's the reason computer can also understand ones and zero. But we cannot understand that. That's the reason we learn some high level languages like C and we code using those high-level languages, and we have translators and compilers which will actually translate this high level to ones and zeros, which can basically be understood by the computer and also work and also make these electronic components work. I said transistors are like cells of a human body, right? So how are the transistors and logic gates related to each other? Now, logic gates are built using these CMOS transistors. If we take transistors to be the cells of a human body, we can consider the logic gates to be like tissues. So we have multiple tissues in our body. Though all of them are made out of cells only, the tissues in your heart are different from the tissues in your stomach. So like that, all of these are made out of transistors only, but the logic gates working differs based on the requirements. So we take a basic building block transistor, we convert it into a logic gate by placing multiple transistors, and using logic gates, we then realize more complex functionalities. Now, how are the transistors being used as logic gates? Let's take one simple example. So we have an inverter here, a NOT gate. What does a NOT gate do? You give whatever input you give, it will invert it and give it out. If you give a 1, it will give out a 0. If you give a 0, it will give out a 1. Now, how is this realized using actual CMOS transistors? If you see the diagram to the right, there is a line called VDD. VDD is nothing but the power supply. Just below the VDD, you have a symbol which has a bubble at the top. That bubbled symbol is actually a PMOS, which is a P-type transistor. And right below that, there is another one which does not have the bubble but looks similar. That is a NMOS transistor. So PMOS and NMOS, like I said, combinedly makes a CMOS transistor. Now, how does this work? We are connecting the bubble and the other one, which is connected together and called as A. That's actually the gate of a transistor. You need not know these terminologies, but I'm just telling it. So when we connect both gates together and we supply the input to that, let's see how it works. Suppose you are giving the input as 1, A is equal to 1. Then the same one will go to the top transistor and the bottom transistor both. The top transistor, being PMOS, will not conduct when A is equal to 1. PMOS conducts when A is equal to 0. So when that does not conduct, only the bottom one conducts. There is no supply from VDD to the output. That's the reason the supply will be cut off and the output will be a 0. So you are getting what you actually desired. You are giving a 1 and you're getting a 0 as the output. Conversely, if you give 0 as the input, then the top transistor starts conducting because it needs a 0 to conduct. When we get the conduction, we will get the VDD to start conducting and we get the output at Q. So we gave a 0 and we got 1 as the output. So this is how a CMOS transistor is used in building a basic NOT gate. Similarly, all the other gates which we saw earlier, like AND gate, OR gate, NOR gate, XOR gate, XNOR gate, everything will be realized using these CMOS transistors only. Now there is another activity for all of you. I'm assuming you are all familiar with the basic gates. With that assumption, there is a small logic gate diagram here. Under these cases where A, B, and C are having different values, I would like you to identify what would be the outputs at each of these points, which is D, E, F, and Y. This is another small activity for you. Now, let us come to how all of these will come together. We learned what is PN junction. We learned how it is used in a transistor. We learned how the transistors are used in making logic gates. Now, how do we use these logic gates to realize complex operations. So that's where the semiconductor industry comes into picture. The semiconductor industry, which is also called as VLSI. I'll tell you what this is in the further slides. Now, all of you might be familiar with something which looks like this green color board with those small black boxes inside. The green color board is actually called as a PCB, which is a printed circuit board. And the black boxes that you see inside, the small ones, they are actually what we are talking about till now. So an assembly of these electronic components like transistors, which are fabricated on a single unit, are called integrated circuits. Those black boxes, which we saw earlier, they are called ICs, integrated circuits, or in simple terms, they are called chips. And the industry which puts all these components together and integrates them, that is called as very large scale integration. That's the semiconductor industry, which will integrate all of these together. Now, what happens exactly in a VLSI industry is the design, development, and manufacturing of these ICs. Now, who does this? There are many tech giants, like some of them which you might be familiar, like Intel, Qualcomm, Samsung, Broadcom. The others you might probably not be familiar, like Broadcom, AMD, ARM, NVIDIA, Texas Instruments, NXP. There are a lot of other service-based companies and startups as well. So there are a lot of people working on semiconductor industry right now. So these are how the semiconductor chips are classified, but I don't think this is relevant right now. You can, this is anyway there in the presentation, you can look into it later. But these are the broad classifications of how an IC is classified into. Let's see why VLSI is important in the first place. Like I said, we have electronic gadgets all around us. And all the electronic gadgets will have VLSI circuits, right from your phones, computers, automobiles, home appliances, all the smart gadgets around you. Everywhere we have VLSI, and it has revolutionized technology. Let's take an example of what you see in the pictures below. To the left, you see a memory card, which is of 16 MB, which is almost 1/4 the size of your palm. And right beside that, you see a SanDisk pen drive, Fire Stick. That's actually a 128 GB stick. So from 16 MB being as big as 1/4 of your palm to having a 128 GB stick, which is almost of the same size, this has not taken a long time. This has been a very drastic change, a very drastic increase. Another very popular example are your mobile phones. Earlier, we used to have huge mobile phones, the size of some walkie talkies. And within a few years, we have very small, sleeker, and powerful machines which we have in our hands right now. So VLSI has revolutionized the industry so much that we have smaller, sleeker, power efficient, powerful, robust, and very high speed devices. So VLSI is it would not be an understatement to say that VLSI is the reason of the modern day development. It would not be an understatement to say that. Let's take another example wherein this is actually the PCB of your smartphone. Let's assume this is the PCB of a normal smartphone. Now we have many of those black boxes, the ICs that you see there, right? And the empty space that you see is actually for the battery. Now we want our phones to have better battery backup. We want our phones to have more features, better camera, better performance, more speed, more number of cores, everything. But we still want them to be smaller, sleeker, lightweighted, and we don't want them to heat up. So when we have all of these requirements put together, then it's very difficult to achieve all of that by having individual chips. So what did we come up with? We come up with something known as a system on chip. wherein we have multiple functionalities put on a single chip. You can imagine this to be like a shopping mall, wherein you have many stores. You have stores which sell clothing, which sell shoes, bags, jewelry, perfume. There are restaurants, there are food courts, there are theaters, everything that you need under one roof in one mall. Similarly, a system on chip is something which encompasses multiple things in one single chip. Now, when I say that, you might be wondering, because we're putting so many things into one, this might be very big, so or the size might increase. But no, these very powerful SOCs are as small as your fingernail or even smaller than your fingernail. This is one example of a Qualcomm Snapdragon 865. This is a processor, a very powerful processor which has billions, not millions, billions of transistors on it, which will perform complex functions, but it is as small as the size of your fingernail. How is this possible? Because this is possible because VLSI industry runs on something called as Moore's law. Now, the gentleman in the picture here, that's Gordon Moore. He was one of the co-founders of Intel. Now, he stated a law when this revolution started out, that the number of transistors per chip would grow exponentially, or rather, it would double every 18 months. 18 months in the sense, almost 2 years. So, every 2 years, you will see the number of transistors on a chip will start doubling. How will that double? Because the size of the transistors are becoming so small. It's almost the size of, close to the size of an atom, I would say. We have such small transistors. Every transistor, that's the reason we are able to stack billions of them on one small chip, which is as small as your fingernail. The entire industry is working based on this Moore's law. But there is a point where Moore's law will also reach, it has come close to that point where Moore's law will also reach a saturation, because you cannot uh, shrink a transistor more than a certain extent. There is only a maximum level wherein it will stop, it has to stop shrinking. But yeah, we are close to that. But still, generally, the industry has followed this law. That's the reason you are able to fit in bigger components. You are able to see small pen drives having multiple GBs of memory available, which was not the case a few years ago. Okay. So, having learned what the industry is doing right now, how the industry is moving, what are the uh, components of a chip, and how the SOCs are built, and how the SOCs work in order to supply multiple things based on the requirements. Let's see what is the life cycle of a chip. This is a very small walkthrough on how this chip actually comes into picture. So it usually starts with the customer or someone who requires something, coming up with a set of specifications, saying, I want this. I want my chip to do uh, points A, B, C, D, E, like some 5 points. I want this to be the outcome. Design something for me. So, keeping those specifications in mind, there is a team which will start modeling that. So, the modeling is usually done in high level languages like C language. Using that, there is a model created which becomes a golden reference. So, here I've taken an example of a full adder. I'm not sure if full adder is something that you are familiar about, but a full adder is something which will take two inputs and one carry input, which is C in this case. It will add the two inputs along with the carry and give the sum output and the carry output. So we have a golden reference there from the system modeling. Now we have a set of architects. architects will actually sit down and discuss how this has to be realized in terms of actual hardware, because we are actually designing hardware here. This is not a software coding. We are designing the actual components. So the architects will sit down and discuss how the hardware has to be designed. Then comes the designing part, where we have designers who will realize this architecture definition into a actual design. But here we use a high level language, an English like language. Usually the most popular ones used are Verilog and System Verilog, but you don't have to worry about that. We just design something which is complying to the architecture definition. Then this undergoes a process of verification at multiple stages, because we will be designing and there are a lot of steps involved. So at every step, we have to verify that the functionality which is required in the first place is kept intact, so that what the end product will be as per our requirement. Then we do something called as a post-synthesis schematic. Sorry, I don't think the figure is quite visible here. But what happens in synthesis is a process wherein the English-like language is converted into gates. The conversion is actually for our reference, because we can't understand, or it is very difficult to design in terms of gates. We'll be designing it in terms of high level language. But what goes in actually are the transistors only, which we discussed earlier in our first few minutes of talk. So we have to actually translate everything that we do into logic gates, and logic gates are basically again translated into transistors. So once we have the final layout of how the transistors are supposed to sit on the chip, we will send that to manufacturing. And where this manufacturing happens is called as a fabrication unit or a fab. Then once the chips are manufactured, they will be then packaged and it will reach us looking like this. These are the final packaged products of the chips. So this was a small walkthrough on what exactly happens from a specification from an idea to an end product. Now, what are the opportunities that you have in this field if you take up electronics engineering? Engineering in electronics is the only option that you can take up. Any branch of engineering which involves electronics. So what are the opportunities that await you if you take this up as your career in the future? You can join some core electronics or telecom industries, or you can join some government organizations like ISRO or DRDO. You can get into research and development, or you can become a teacher, academics. We are in need of good teachers, so you can join academics. There are some software development also needed in the VLSI chip life cycle. So you can either choose software development as well, or you can pursue a higher education after engineering. You might probably do MTech or MS, or later you can even do PhD. So there are multiple options that you can take up, or you can choose to do it as a hobby as well. There are people who take up Raspberry Pi boards and pursue it as a hobby electronics. So there are multiple career options if you take up electronics, and especially VLSI as your specialization, which will help you in your career. With that, I would like to conclude my talk, and sorry again for joining late because there was a issue with the network. Once again, I would like to thank KSTA, Dr. Ramesh, and all the other people for giving me this opportunity.
Deepthi, thank you very much for a very nice presentation on semiconductors. background of semiconductors, and also career opportunity for students. Here all they get opportunities if they. It was an excellent presentation.
Thank
We
you.
have placed here and so the participants, I thank you. Time and all. Now let us see if there are any questions. Please answer them.
Sure.
Umesh Gatke, any questions are there?
Sir, there are no questions, sir. Requested them to post in the chat box, but they have not questions as of now. Sure, they may ask that time we can communicate with them.
Please
Sir.
questions out of your talk, and we'll be posting them on our WhatsApp group, and students will answer those questions, and the answers will be sent to you. You have to select 2 best answers.
Sure, sir, definitely. And I'll be happy to take up if there are any other questions also offline.
Yeah. If there are any questions, we'll be forwarding it to you. Kindly answer.
Sure, sir. Definitely.
Second, we are very grateful to you, and you are a very good speaker. Friends, I am sure would have got a lot of take-home message from your talk. In fact, semiconductors is one of the topics that your talk will be of and I'm sure they would have got information that they intend to get from your talk. Thank you very much.
Thank you, sir. Thank you again.